So I have to. I think so. Okay. And then I'll talk about a little bit about gravity, how this is generalized to gravity. And finally, I will describe our work and my work in this group, a part of the work, which is related to supergravity. How to generalize this to supergravity. Supergravity and how to consider fermionic symmetries, which is well, it's very difficult actually. We have been working on this for almost 1 year, almost a year. It's a very difficult problem, but we have finally, like 1 month ago, we finally found a solution. And well, the paper has been accepted just today. So I will briefly show how work is proceeded, and I will go very fast in the last part of supergravity. More. So a very brief introduction. Now we talk about the BMS symmetry. The BMS symmetry is a direct product of semi-direct product of the Lorentz group and the super translations. The super translations are infinite dimensional extension of the usual translations, where you span in modes, the first four term are the usual translations to 4 dimensions. This group, the BMS group, was found a long time ago, in the 60s, in the context of gravity, without cosmological concept of flat gravity, in the context of asymptotic symmetries of general relativity, specifically in the context of gravitational waves. So this is a asymptotic symmetry group when you are considering so when you are approaching to null infinity, the null infinity part of the Minkowski space. Now it was possible that in 1974, this paper by Javier and Tempon, they performed the same computation, or actually it was a very same idea, but in a different way, because they were using the Hamiltonian formalism, which is going to be the formalism that I'm going to use in that we have been using, and I will show how to use it. And when you perform the same computation, so general relativity in the Hamiltonian form, at the spatial infinity, they found that the asymptotic symmetry algebra is just Poincaré. They couldn't find the super translation symmetry, which is possible because in principle the BMS symmetry should be a symmetry of the theory. So it should not be related to gravitational waves. So that was possible. Now, very recently, in 2018, 2019, Marguerite and Cédric Tossat, both from Belgium, they found a way to resolve this problem. And the problem was solved by considering some extension of the asymptotic conditions. So asymptotic condition means how you have to define how the fields follow at infinity. So they have imposed a different boundary condition with these twisted parity conditions. I will say something about that later. And in this way, they were able to find the BMS for algebra in the asymptotic spatial infinity, the asymptotic symmetry analysis at spatial infinity. And now we'll talk about this. Actually, this is the first part of this talk. And then the idea of this talk is to briefly describe the procedure, the approach, and then at the end I will talk about our work in supergravity. There are some other papers using the same approach, Javier, for example, but I think that I will say something about it later. And also generalization to higher dimensions, but I will try to say something if I have time. Okay, so the simplest case, of course, is electromagnetism. For that, you have the reference. The starting point of this approach is the Hamiltonian form, the Hamiltonian formalism. The Hamiltonian action for electromagnetism is given by this expression here, where we have the vector potential, it's going to be momentum, and some constraint, which is the Gauss constraint, and it's Lagrange multiplier. It's the usual. This is well known. Here you have an extra piece here, which is a boundary term. This is the boundary of the spacetime, and it's there in order to have a well-defined variational piece. Usually, in the usual, let's say, the usual approach, or the usual approach, you have to say, of course, how is the follow-up of these fields of the fields that are in the theory. You can always say that the field decays, let's say, as 1 over r squared, meaning that this term is going to be zero. It's not there. But if you consider this fold, for example, which is the usual one for in the context of asymptotic symmetry, the vector potential goes like 1 over r, and the conjugate momentum goes like 1 over r squared. But well, these functions are functions of the two sphere. Just depend on the angles, of course. We are in the Hamiltonian formalism hole, so we have the split in the two space and time splitting. So this index runs only for the coordinates and not for the time. The time is over there in the dots. Now we have this. Of course, this is the usual constraint, the Hamiltonian and everything. But we have to be sure that this part, which is the kinetic term, is finite. So we can say, let's say we have AI goes like r to the 5, let's say, something very crazy. And of course, if you put this here, this term is going to be divergent on r when you go to infinity. You have to take r goes to infinity. So this cannot be anything. We have to choose wisely. And you see that the next slide. Well, we have to be sure about that, and we'll say something about that in the next slide. But it's important to say that this action has some is invariant under some gauge symmetry described by this expression here, where the vector potential transformed in this way, where this parameter depends on the angles, and the conjugate momentum transformed in this way. So the action is invariant under this gauge transformation. This transformation is generated by this chart, this generator, where you see the bulk part, which is the constraint, and when you are in the surface of constraints, this term is obviously zero, and you get only the boundary term, the two-dimensional part, the surface integral, which is different to zero. And of course, if you, for example, in this coordinate, if you set epsilon equal to 0, you recover the electric charge. This is the conserved charge. The particular for this selection, this is exactly the electric charge. I will talk about several times about the improper gauge transformations. You can have proper and improper gauge transformation, meaning that the improper gauge transformation has charge different to 0. So you will have some gauge transformation, but where this charge, for example, which is the relevant one, is 0. But in this case, this is an improper gauge transformation because the charge is different to 0. It generates something that changes the physics, because the conserved charge is different to 0. So it's very important to understand this concept. Now, you were very generic deformation of the time hypersurface, constant time hypersurface, can be parameterized by the normal and tangential components. In particular, well, they are defined by these two parameters. In particular, you can specify this for Poincaré. In this case, you have this expression here. You have the Lorentz boost, the standard translation, which is A pair and AI, and the spatial rotations. Parameterizing this way, the field transforming this way by this deformation. We have the parameters, and we always have this gauge freedom that is going to be used. It's very important. It's always important in order to fix some problems. And it's not relevant at this point. We can go to spherical coordinates. This is just a technicality. The field transforms in this way in spherical coordinates. but it's important to comment here. Well, this is the same, but the same as before, but in spherical coordinates. Here we have the D is the D and I are the Lorentz, homogeneous Lorentz transformation. T and W are translations. Here, T and W can be angle-dependent functions, but in particular for the Poincaré case, of course, these functions has to satisfy the Killian equations, which are this one over there. This is just for the zero modes, I say, just for the Poincaré algebra. And it's important to comment here, and this is going to be very important in this talk. It's about the parity of the functions under antipodal map. Why is that? I will show you that later. But this is how it's defined in this context, the antipodal map. We have a circle and we are considering antipodal points. And then it's going to be very important. But it's important to comment that these functions are odd under parity, meaning that when you perform this map, antipodal map, they change the sign when they are odd. Now, as I mentioned, when it was first, we have to check that the symplectic form is finite. If you replace the specific value of the follow of the fields by R, ER, and by AI, you will see that there is a logarithmic divergence. There is a 1 over R. You have to integrate over R, and this is going to generate a logarithmic divergence, right, which is terrible. So we have to deal with that. And the way to deal with that, we have to is by imposing some parity condition on the functions. How? For example, for the radial components, we can impose that the AR has this odd under parity, there is a change of sign. And for the pi, this is even under parity. Of course, this is compatible with the known solution with gauge invariant, and also the charge is going to be, because pi r is odd, is even, sorry. This is the only non-trivial charge is going to be generated by the even part of the parameter. So we can do the same for the angular components. And you see that this is why it's important to impose these parity conditions, because they have opposite parity. So you replace this here, and this is going to be odd under parity, meaning that when you integrate under the circle, this is going to be zero. You will have a cancellation because of that. So that's the reason, because it's important to impose the parity conditions. So in this way,
I understand. So pi is the electric field. So it's a physical quantity that I can measure locally, gauge invariant and everything. Isn't this a very big restriction that you only look at configurations which have some parity symmetry?
No, they are compatible with the known solutions, with all of them. There is no restriction. This is the usual. This is usual. It's not different to the usual electromagnetism.
If I have a distribution of charge that doesn't have any parity symmetry, like a potato,
I see.
Okay.
Okay. Well, I can say that this is compatible with the usual solutions. I agree that maybe this is not it's not true that this is compatible with every solution. But I'm not completely sure.
But it refers only to things.
Well, yes, that's true. So yeah, that's true. Yeah, sorry, you're right. So this is compatible with this. This is our asymptotic conditions. So you see, if you have a weird, let's say a weird distribution, and this is going to be a point particle at infinity. We have an observer at infinity, and this is going to be a point particle from the point of view of the observer. So I think that this is going to be compatible with solutions at infinity. This is clear or not?
Well, I don't know, because I'm not sure what freedom do you have to impose this. If there's no physics in it, then why should I impose this condition?
You have to impose them because you have something that is not finite. And that's a problem. You have an action, the action is not finite. It's a divergence when you go to infinity. And at infinity, you measure the charges, the conserved charges at infinity. integrated. Yeah.
Yeah, but that's the
So it's
integral.
and it's physical, it's what you measure.
That's the integral of the electric field.
Yes, and you do it at infinity.
But it doesn't have to be symmetric under any symmetry for that integral to be finite. But, I'm just wondering if there is some restriction here of physical nature.
I see. I think there is no restriction, but let me think about it. That's a good question. So we can do the same for the angular component, but here is a bit different, and this is the origin of the enhancement of the symmetry, because you have, let's use a usual asymptotic condition for the electric field. You will not get an infinite dimensional U1. I will say something about it later, but in the usual computation, you do not get an infinite dimensional algebra. You do not get VMS for electromagnetism. And the important thing here is to use this twisted parity condition. This is twisted because you have an extra piece that goes as a pH transformation, only for the angular component. Again, this is compatible with the solutions, how the solution decays of infinity. And you have to impose an extra condition, which is also compatible with everything. This is part of the constraint. This is all this, you have a bar here, so this is an asymptotic field. This is how the field decays. It's not the field at the bulk, it's just how the decays and infinity. It's the 1/r component. So here it's important that we have some twisted parity condition with an extra piece, and these pieces they have a different parity. So this is odd and this is even under parity. Of course, this is not for free. You will have to do something in order to cure some problems. But interestingly, because of the parities, you can put this here back in this expression, and this is 0. So there is no logarithmic divergence. Of course, you have to impose an extra condition in order to have this, otherwise it's not true. But everything is compatible with this, how the solution decays at infinity, at the spatial infinity. Now, if we want to have we have the theory, and we want the theory to be invariant at the Poincare. You really need that. It's very important. Now, this is the usual procedure. It's very well known in classical mechanics. Not so crazy. You have this symplectic structure. Okay? You can start this from the kinetic term. It's just given by this expression here. It has the vector potential and its conjugate momentum. Now you have this. You have to prove that this is invariant under the Poincare. Meaning that I will go to the next. So a transformation that is canonical is transformation is canonical only if this equation is skipped. So you have to take the contraction of the symplectic structure, and this is going to be, if this is 0, the transformation generated by this vector field x is canonical, which is very important. Now we have modified the asymptotic conditions. So if we perform this computation, we will get something that is different to 0. In the previous case, let's say with the previous asymptotic condition, this was 0 because it has a parity, well-defined parity. But now this is a twisted parity. It has a twisted parity condition, meaning that this is going to be different to 0. That means that the boost in particular, which is always the problem, is not canonical. And we have to cure this problem. Otherwise, the theory is not invariant under Poincare, under full Poincare. So we have to do something with that. And the way to solve this problem is by adding some surface degree of freedom at infinity. You see that this problem is a problem at infinity in the surface. It's in the two-dimensional surface. So we can add some field that lives only at infinity in the surface in order to prove this problem. And this is the field. This has a definite parity, which is odd, and transforms in a very precise way. So what we are doing, we are, let me go to the very beginning. So we have, I'm sorry for this. We have this, which was the kinetic term, the usual kinetic term, and we are adding something that lives only at infinity, at the surface. which is given exactly by this expression here. So this expression here with this field, extra field, which is only at infinity, and this transformation gives exactly this extra piece here, meaning that the proofs are now canonical. Of course, there is a modification, so the field transform a little bit different, but it's compatible. Of course, everything is compatible. So now we have the symplectic form, which is invariant, and a boost-defined canonical transformation. The problem has been cured in this way. And this is not an artifact. This is going to be very important, and we'll talk about this in the next slide. Now we can always do the following. It's a technicality, it's not important. We can always clear this field in the boundary, and we can extend this surface field to the bulk by adding some constraint and Lagrange multiplier, which is again this way in the action. So we have an extra piece. And this extra piece has it's just a constraint, so it's not going to modify the dynamics in the bulk. It's not problematic. It's just to have something that is more symmetrical. Now it's very interesting that this action, because we have added some extra piece here, this is extra. Now the action has an extra gauge invariance, which is parameterized by this new field here. So this was the usual, the previous one. Now we have an extra gauge invariance. Of course, we will have an extra gauge invariance. We will have a generator, a canonical generator, and the canonical generator has now these two parameters here. So it's the usual one plus some extra piece. This is the even part, and this is the odd, and both are improper gauge transformation because the charge is different to zero. Now it's very interesting because we have more symmetries. We have an enhancement of symmetry. This was the usual thing, and now we have some extra piece. But you can perform an interesting. I will not talk about this because I do not have time. But in this paper by Mark and Cedric, they proved that you can go to some hyperbolic coordinates, and you can in this hyperbolic coordinate you can make a connection between the spatial infinity and the null infinity. And if you make this connection, it's not so direct, you have to integrate, and it's not so easy to do it. That's the reason, because I'm not going to talk about that today. You can perform this procedure, and you will see that these two, the even and odd part, these two functions, combine in a very precise way in order to generate the full angle-dependent U1 transformation at null infinity. So at null infinity, you have one parameter that parameterizes this U1 infinite dimensional U1 transformation. And if you make the connection, you really need both in order to make the connection. So this extra boundary field is not there because it's not an artifact. It's very important. Otherwise, the connection is not direct. There is no connection. Well, the algebra, now everything is canonical. All the generators are well defined. We have a boundary term, this boundary term, the surface term. We generate the symmetry, the algebra. And the algebra of the generator is given by this expression here. This is the Poincaré. This is a U1 generator, this G, the one defined previously. And the algebra is finally a semi-direct sum of the Poincaré algebra and the abelian algebra parameterized by these two mu and epsilon bar, which are angle-dependent U1 transformation. So this is the electromagnetism version of the BM algebra. We have a U1 angle-dependent infinite dimensional symmetry. So this is the way you recover this infinite dimensional algebra at spatial infinity.
So when you say semi-direct sum of Poincaré algebra and abelian algebra, you mean like there are two
this is the abelian,
or they are direct products? Ah, okay, it's the
algebra. The abelian, yes, okay. You see this one. Yeah, okay. This is going to, this is given here. Okay, so this is the procedure. You have to modify the asymptotic conditions. The modification of the asymptotic condition makes the boost non-canonical. You have to solve that. In order to solve that, you add an extra boundary field. And the boundary field, because you have an extra boundary field, the action has an extra symmetry, and the extra symmetry is going to generate the extra the parameter is going to generate the extra U1 symmetry that is needed in order to make the connection with null infinity. So it's very, very important. Okay, so let's move to gravity. Still have some time. Of course, gravity is a interacting theory. It's quite non-trivial. It's highly nonlinear. So it's the previous theory was very simple. It's just electromagnetism. But now we have gravity in this Hamiltonian action for gravity. What do we have here? We have the spatial metric, the conjugate momentum, the lapse, the shift, the Hamiltonian constraint, and the momentum constraint. We have more indices, we have more structure, we have interactions. So it's, of course, it's quite different. And of course, we have this extra boundary term here that is there in order to have a well-defined action field. Would be zero if the field became very fast. But the idea is to have something that is different to zero. This is going to generate the asymptotic symmetry algebra. In the usual, let's say the usual asymptotic conditions are given by this expression here. Yes, this eta is just the metric, the Minkowski metric, and the metric goes like 1 over r, and the conjugate momenta goes like 1 over r squared. Of course, this function depends on the angles. Where this is the result, or this is the follow-up of the paper of Javier and Teichenbaum that I talked at the very beginning of the talk. And it's interesting because, of course, you have to impose some parity conditions, which is given by this expression here. And because of the parity, this term, which is again a logarithmic divergence, is zero. In the same way as electromagnetism. The problem with this approach, the approach in that paper of 1976, is that in order to have some coordinate system that where this parity holds, you see that the parity is very precise for every component of the metric and the conjugate momentum. You have to perform some improper gauge transformation. Yeah? The proper gauge transformation changes physics. Yeah? And so the charge is equal to zero. So this is not the correct way to impose parity conditions, because it's not compatible with physics at the end of the day. How do we solve this, or how actually Mark and Cedric solve this problem? Is by adding some gauge transformation here, making this compatible. And this is the precise way. Again, we have some twisted parity conditions. We have the even and odd part, and some gauge transformation with a very precise parity for every function. This accommodates, for example, the tap nut or charge and every solution of general relativity. There is no problem there. Of course, as in the same way as electromagnetism, adding some extra pieces in the asymptotic condition is going to spoil a lot of things. In particular, it's very nice because the solution is simpler than electromagnetism. Some problems, for example, the divergences in the symplectic term can be solved by imposing some extra conditions on the constraint. So saying that the constraint in the case is 1 over r to the 5, both of them, which is okay with the solution because the constraint has to be zero. So there is no problem here. But this is going to give us some extra conditions, extra equations. And there is also another problem. So with the symplectic condition that are defined this way, you can have some problem with boost in the same way as electromagnetism. But it's very interesting that this problem can be solved by killing one of the components, the RA, the R angular component. So there is no need to add an extra boundary field. The problem can be solved just in this way. It's simple. We don't know why, because if you go to higher dimensions, you have to impose that. If you go to higher dimensions in electromagnetism, you also have to impose. But gravity in 4 dimensions is special for some reason. Gravity in 5 dimensions, you have to do something else. Something that we do not understand. But all the problems that I shown in the electromagnetism case can be solved with these 2 extra conditions, which are compatible with solutions to that. So there is no problem. In the same way as electromagnetism, now there are more indices. The structure we have more structure. So under some deformation of a hypersurface, which is parameterized by the same parameter, the fields transforms in this way, the metric and the conjugate momentum. Again, you have the parameters, the asymptotic expansion of the parameters is given by this expression here. Again, you have the rules, spatial rotation and everything, but you have an extra freedom here. And this extra freedom, I will not specify with the equations, but I can say that these extra pieces here, which are the sub-leading, and actually they are field-dependent gauge transformation, are here in order to have a well-defined generator, and this extra condition here is in order to maintain the HRA equal to 0. Of course, if you put here delta HRA, this is in the right-hand side, this is not going to be 0. So you have this extra freedom here against transformation that you can, with this very precise parameter, in order to have this to 0. Again, everything is canonical, so the generator is well defined and is given by this expression here. This is quite general. This is from the paper of Javier. And as I mentioned, the generator is fine, integral, and canonical. And the algebra is the following. It's very simple. It's the same. It's just the algebra of the generator is given by this expression here. The important thing here is that we have these two parameters, T and W, which now are angle dependent. So if T and W were just constant, so for T and W constant, you recover the Poincaré algebra. But here T and W depends on the angles, and this is going to give us the BMS algebra. So this algebra here with these parameters is given the BMS4 algebra in an unfamiliar parametrization. Yes? You have two functions, T and W instead of just one, which is the usual BMS algebra in 4 dimensions in the analysis at null infinity. Okay, so again, the asymptotic condition had to be modified with some twisted parity conditions, and this twisted parity condition allowed to obtain the asymptotic symmetry algebra, the BMS4, the asymptotic symmetry algebra of gravity at the spatial infinity. So this result is from 2 years ago, 3 years ago. So now we can say that this is not just so the BMS4 algebra is not related to gravitational waves. It's a symmetry of the asymptotic symmetry of the theory. It's not just because they are gravitational waves. So it's very important, the result actually. It was very fast because why this was not working. Okay. Again, in the same way as electromagnetism, now we have two functions, W and T, and they combine in a very precise way in order to make the connection with null infinity, where there's only one function. So everything's working well, and again, you need both W and T in order to make sense of the result at null infinity. And now one of them is not, in the previous case, the function was coming from this extra boundary field. In this case, coming from another, it's not the same origin, but it's there. This is probably the reason because you don't need the extra degree of freedom at the boundary. So we have some time. So the question is, well, there are some. I will mention something about that at the end of the talk, but there are some extension to electromagnetism in higher dimensions, for example. For example, for the spin 2 case, just a free field. There's also some extension that we did some time ago, the last year. And there is also another paper from another group where they performed the same computation for Young-Mills. And for some reason, it's not clear. There is no. So in the analysis of Young-Mills at null infinity, you have an infinite dimensional algebra, some BMS algebra for Young-Mills. But at the spatial infinity, they couldn't find the infinite dimensional algebra for giant. But I'm not going to talk about that because it's not right. But there are some other results. And so we were wondering what else we can, well, I don't know, we can think about higher spins, for example. We can because at null infinity there are several results. So you have an infinite dimensional algebra, BMS algebra for higher spins fields, for example, and also for supergravity. So we were thinking about supergravity. And in supergravity, again, I will not say something about the theory because it's very well known. But this is the action of supergravity, Hamiltonian action for the n equals 1 supergravity 4 dimensions. Here you have, well, you have to go to field lines to try it and conjugate momentum. This is more the best way to solve the problem in supergravity. You have the gravitino, the split trihalf field. Again, you have the lapse, the shift, and some fermionic constraint, and again, a boundary term, which is very important, as I mentioned before. Here we have the full interactive theory, so we have full interactive supergravity, meaning that the constraints are modified by some fermionic terms, those quadratic in fairness and also with the spin connection. But at least for this case, which is the first one I will show, these are not going to contribute because they decay too fast. So we have the same as before for gravity, but we have some extra constraint, the constraint that generates supersymmetry, local supersymmetry, which is given by this expression here. Again, we have some extra contribution that they're not going to contribute because they decay too fast. So we have supergravity, it's Hamiltonian form, and it's described by this action. And we have an extra symmetry, which is the local supersymmetry, generated by this parameter, which is not here, and it's going to be in the next slide. Just a comment, this is a paper, this is a first paper on supergravity, and this collaboration is from the last year, I think. Yes. Now we are dealing with field lines. We are in so we have to say something about that. We have a freedom that we have to fix. Yes, we have the freedom. We have to freeze some freedom in order to attach this to Cartesian coordinates, Cartesian frame. You have to fix it. You have to say something about the frame, and we did it in this way. We are using the time something frame, but this frame allows us to describe the fall-off of the triad and the conjugate momentum by the same functions as before. Right? So we have to specify this piece here, this hij and pi ij, which are exactly as the same as before for gr. So it's quite easy computation. It's not crazy, but we have more freedom because we are working in this format. So now we want to impose some boundary conditions. So the follow for the gravitational field, and there are some requirements, like the usual one that I have mentioned before. They should make the action finite. They should be invariant at the lower supersymmetry, defined by some parameter. Which is in this case has to be constant at infinity, a constant spinor at infinity. I'm working with the Majorana fairness, just in case. And of course, they should make the surface integral fine. We have to find everything has to be final and canonical. And the usual way to find the follow for the gravity is that this goes like 1 over r squared. You plug in this in the action. So let me go back. So you put it here and over there. Since this goes like 1 over r squared, and everything here is going to be fine. Okay? There is no problem with the kinetic term here. It's fine. There is no logarithmic divergence as before. Okay. the asymptotic conditions are invariant under supersymmetry, parameterized by this parameter epsilon 0, which in this case is constant. And I will say what should be constant. Transforms, provided that the field transforms in this way. The metric, the conjugate momentum, and the gravitational field. Why do we have this? If you can see here, this transformation, the very last one, this field goes like 1 over r squared. So let's suppose that this epsilon depends on the angles. If this epsilon depends on the angles, this guy is going to go as 1 over r, which is not compatible with the transformation. Okay? So it's a problem. So you have to impose that this is equal to 0. For this asymptotic condition, if this goes like 1 over r squared. So this parameter must be 0, must be constant, sorry. And because this is constant, this is not going to give us an infinite dimensional asymptotic symmetry, fermionic symmetry, which is what we are looking for. I didn't say anything about 3 dimensions, but if you go to 3 dimensions, so supergravity in 3 dimensions, you can get some super BMS algebra in 3 dimensions. And that algebra has some infinite dimensional fermionic symmetry. So what we are trying to find here is an infinite dimensional fermionic symmetry. And in this approach, with these asymptotic conditions, you cannot get that. You will get that the parameter is a constant, should be a constant. So if you perform, it is interesting because these asymptotic conditions are not only invariant under super Poincare algebra, but you can also have BMS super translations. So that's why you go to the next slide. You have, again, everything is well defined, the generator and everything. You have this generator, the SUSY generator of the supersymmetry, which is the new one, the new piece with respect to the previous one. This is the gravity part plus supersymmetry. And the algebra is again given by this expression here, where now the fermionic parameter, as I mentioned, depends, is a constant, meaning that there are only four components. Okay? It's not there are no infinitely many parameters. It's just, so there are just 4 because we're in 4 dimensions. So this is the first, well, this is the canonical realization of the super BMS algebra that was found by these authors in 1986, where the fermionic parameter is a constant. It's not an infinite dimensional algebra, fermionic symmetry. So we have been working very hard the last year in order to have this parameter different to a constant. And that has taken like 1 year. It's very, very difficult to problem. Because you have nonlinear terms, you have quadratic cubic terms. It's really a mess, but we were able to solve the problem. But for that, we went through the free theory first. Okay? So we were wondering, can we define some infinite dimensional fermionic symmetry? And we solved the problem at the first. We solved the problem for the free theory. And I will show, so we will start with the Rarito-Schwinger theory. It's just the theory of a gravitino, free gravitino. The 4 dimensions. Again, you have the constraint and everything. So it's as before. There is no metric here, so it's a free theory. The standard asymptotic conditions say that this goes like 1 over r squared. We will get the same as before. We will not get nothing. Just super Poincare as the asymptotic symmetry algebra. So what we have proposed? We have proposed that the gravitino field can be split in this way, where we have added some extra piece, which is just the gradient of a function that is of order 0 in the R expansion. Okay? So we have some extra piece that goes exactly as a gradient. And this is important. If you put here something that is just a function without the derivative, you will get some divergences and everything is going to be a mess. So you really need to have this derivative here because you have to integrate by parts. And integration by parts is going to kill the problematic term. So this is our proposal for the free theory. Of course, if you add this extra piece, you will have some modification that's in the kinetic term. The modification of the kinetic term are going to produce some problem on the boost in the same way as electromagnetism, but the problem can be solved again by adding some boundary field, which is in this case a fermionic boundary field called omega. So the problem with the boost can be solved in this way. So with this extra field chi, this extra boundary field omega, we can define this generator. This is the supersymmetry generator, which has 3 parameters now: epsilon. This epsilon depends is a constant, which is which we could have epsilon 0 here. But this epsilon and this set, they depend on the angles, and this is going to generate some asymptotic, some infinite dimensional fermionic symmetry. These 2 parameters. The algebra is just this one, so it's Poincaré. This is a fermionic, infinite dimensional fermionic symmetry. And interestingly, there is a central charge because of the structure of the generator, the fermionic generator. So we were able by extending a little bit the field, splitting the field in this way, we were able to have an infinite dimensional fermionic symmetry for the field theory. Now, and this is compatible with the. You see, this is a fermionic symmetry, but it's a gauge symmetry. It's not supersymmetry. It's a fermionic gauge symmetry, and you can just consider the both spin 2 and spin 3 have free actions, and then you can consider supersymmetry. So they are related by supersymmetry transformation, and this formulation is compatible with that. Okay? This is a free theory. Now, this was a very hard problem to solve. So now let's consider the local supersymmetry, local supergravity, local supersymmetry, full supergravity, not the free theory. And we have learned that we can modify the way that we can generate some fermionic, infinite dimensional fermionic symmetry is by adding some extra piece. Now we are in the interactive theory, so this is the covariant derivative. This contains everything, the proportion, everything. If we do this, well, this goes like over 1, and this goes like 1 over r squared. Of course, since we have added this term, it's going to be a mess. So we will have a lot of terms. You remember that there were some quadratic terms in fermions and spin connections. It's really a mess. You have a lot of terms, Blacksford and Blacksford of terms. It's very beautiful how we solve the problem, but it was very hard to get the result. Again, some modification of the congruent momentum. This contains some kinds, some pieces with this term here. Again, there are some problems that again can be solved by adding some boundary term, this omega transpose. This is the Hamiltonian action. This part of here, this is the kinetic term, this is the Hamiltonian. Here we have, this is the usual fermionic constraint with the covariant derivative and everything. So it has a lot of terms. And we have this extra constraint where this F, this F constraint all the chi contribution. So here you have, since you have this, you have to put this in the kinetic term, and this you have to perform a lot of integration by parts, and this is what you get at the end of the day. Something that depends on an extra constraint, which an extra constraint that involves only the chi contributions with Hamiltonian. You have that. Then the supersymmetry generator is given by this expression here. So the usual thing is just epsilon times the constraint plus some boundary term, which is going to be generated. It's going to be the generator of the asymptotic symmetry. So you have, but as I mentioned before, you have to impose some extra conditions, and these extra conditions are imposed by adding these extra two pieces, which goes with the constraint in the fermionic constraint. So these are going to be field-dependent gauge transformations generated by HI and this F. Why do we need to do? Why do we need to add these extra pieces? It's because you have to maintain this condition HRA equal to 0. That can be maintained by adding this extra piece here. So you replace this here, use a momentum constraint, and you make the transformation to maintain this condition. And also, if you want to impose that this guy 0 has no zero mode, meaning that there is no chi constant, because the chi constant is given by this epsilon. I will show that later. So this is could be a technicality, but it's very important for the correct result when you close the algorithm. So this is the fermionic generator, the bulk, and the extra piece, which is in the boundary, is given by this expression here. So getting this result took like 1 year. And it's very nice because this epsilon 0 is a constant part. There is no, this is as a previous case, but you have this epsilon, which is a angle dependent parameter. And you can see here that when you set epsilon equal to epsilon 0, you recover the usual charge for the previous case when you. So with this charge, you recover the super poincaré. But now we have some epsilon parameter that depends on the angles, and this is the result that we were trying to get, is that when you compute the algebra of the generators, of both fermionic generators, of both supersymmetry generators, you get at the right-hand side the super translations. So in the previous case, when you compute the algebra, the bracket of the fermionic of the supersymmetry generator, you just get the translation, the usual translation, the usual part of the super poincaré algebra. But now with this enhancement, we were able to get the super translation on the right hand side, which is what we were looking for. This is the structure that you have in dimensions. And also it's a structure that there are in some papers at null infinity. There are also some papers at null infinity in the context of supergravity. Well, parameters transforms in this way, but this is the important result. So we were able to do that. And some remarks, well, just some extra comment, as I mentioned before, there are a lot of papers on higher dimensions, but in the concept of electromagnetism in higher dimensions. There are some funny things there. We are about to finish a paper on supergravity in higher dimensions. There is something interesting there because there are some problems, and at null infinity you cannot have BMS in any dimensions. So in 4 dimensions you have BMS, but in 5 dimensions you cannot have, because there are some logarithmic divergence. You have to deal with some divergence. So you are not able to get BMS for gravity in 5 dimensions. And in the analysis at null infinity. And we're about to, we performed this computation for gravity in 5 dimensions at spatial infinity, and we were able to get the algebra. So it's a bit puzzled why we have the result in spatial infinity, but in null infinity is not possible. So there is something that we have to understand there. You can do the same for Einstein-Maxwell, for example. You will have some semi-direct sum of DMS4 with the angle dependent you want. So you have something that's compatible with the Einstein-Maxwell's charged black holes. And well, there are some comments on at null infinity. The comments are that as I mentioned before, you can go to hyperbolic coordinates and perform some very precise algorithm, let's say, some very precise approach in order to connect both null infinity and spatial infinity. And they have found that this extra U1 symmetry, or this extra generator parameter in the case of gravity are very important in order to make the connection. So it's very, very important to have these extra fields and everything in the case. Well, we are working on this in some detail because the last paper that I showed the previous slide it's a letter. It's just we're just showing the result. So we're working on the full paper, which is going to be very long because it's a long computation. Yeah, we are also thinking about extended supergravity. So we have extended supergravity. The structure is richer. It's very nice also. But there are some technical problems because it's not so easy to find. Actually, there is no paper with the Hamiltonian formulation of supergravity, let's say n equals 4 and n equals 8 supergravity in 4 dimensions. So it's a long computation. Okay. So this is what I wanted to say.
Okay, thank you. So other questions?
Okay, when you go to third dimensions, it's not very clear to me the meaning of going to spatial infinity, because you know that there should be those extra dimensions should be compactified. So
well, it's not in that context. I know that we live in 4 dimensions. No, but we're not dealing with compactified dimensions. We are just extending the theory to higher dimensions. So it's just general relativity in 5 dimensions, but we are not dealing with the extra dimension. I understand the point and the question, but we're not thinking about that. But it's a good question. Yes, what happened with the extra dimensions? Yes, we're just trying to understand what happened when we go to higher dimensions. But it's a very good question. Actually, we have to make that question. It's important for. Otherwise, it doesn't make sense. Yeah? But thank you for the question. Yes.
Is there a Lagrangian formulation of this?
No. No. Oh, well, for yes, but there is a Lagrangian. Well, actually, at null infinity, it's a Lagrangian formulation. It's a covariant formulation. Yes, so there is a definition of a charge which is covariant. But well, the result of the procedure depends on the Hamiltonian formulation. So, but I don't know. There is no Lagrangian formulation.
Okay, another thing I want to ask. So basically, the message, if I understood correctly, is that you expect the same DMS algebra to be present at null infinity and spatial infinity in whatever case. Okay, so this is an asymptotic property of your theory. Okay.
So it cannot be related to gravitational waves. It doesn't make could make sense, but there is not just to gravitational waves. Yes. Now we are at spatial infinity. We have it's not related to gravitational waves. It's a Cauchy surface. Well, also the problem is very well defined. We have evolution of Cauchy surfaces. It's more robust. The problem defined this way. At null infinities. But
I have another question. The VMS algebra has been used in the context of black hole horizons, because they are null purposes, I suppose. But can it be possible to use this at the spatial surface, like at the main wall?
A very good question.
Something like that.
Yes, could be. Yes, of course. If you have the surface, you can see what happened. Yes, it's a very good question, but I do not have an answer. I think maybe you are the first person that I have talked about that. I don't know. I don't know any paper about that.
More questions? Questions from the guy in Zoom?
Maybe there is nobody in Zoom.
No, yes.
No, I'm in there, but I have no questions.
Okay, thank you.
Okay, I didn't understand one thing, a very naive question.
Let's try to.
You assign a VMS algebra to spatial infinity. The slogan is that the essential thing is the super translations, which are defined as total shifts in the null variable, and parameterizes the null infinity. So, should we call it VMS or shouldn't we have
Well, it's the same algebra, parameterized in a different way.
name or something?
In principle, it's the same algebra. It's exactly the same algebra, but it's parameterized in a different way. But it's the same algebra. It's really the same algebra. They Cedric and Marco proved that the same algebra by doing this analysis in hyperbolic coordinates. You can see that it's exactly the same algebra. So it's VMS. Yes. From an algebraic point of view.
Okay. Geometrically is not, but
Exactly,
algebraically
yes.
it is. And another very general one. What is VMS useful for? Let's say if you are looking at, say, the S matrix of scattering of gravitons. Let's say.
Yes, well, there is the paper, the original paper is from the 60s. Just a few, well, let's say just a few people were working on VMS in the, let's say, 30 years. One of them was Glenn Barnich, which is at the ULB, and also Ashtegard. But this was just a few people working on that, trying to understand the VMS symmetry, the VMS algebra, at an infinity always. But then some years ago, Strominger found this relationship with the.
I know.
Yes. So this is.
My question is, what did Strominger achieve?
It's not clear. No, it's not clear. Let's say. No, I'm not an expert on that. But no, I don't know. It has mutated in a very. No, it's very nice, but no, I'm not sure. I'm not sure what's this. One in principle, that one of the idea was this was related to information paradox. As you mentioned, there was a relation to the horizon of the black hole. Well, all these world identities and everything, which is another thing that's also very important. But it has mutated in a very nice way, actually. But yes, I cannot say something more specific about that. But it's a nice area. Sorry?
No, I mean that if you have, say, conformal symmetry, for example, you get more constraints on the physical variables, the physical quantities of relation functions, let's say. And you have non-trivial equations that are difficult to satisfy, and you ask, can I find a solution, etc.
No, of course.
And this matrix, if you just have Poincaré, is a little bit more than just saying that you have to write it in terms of Mandelstam invariants. But if you have this extra symmetry, does it introduce some nonlinear constraint into this matrix element that can be solved by bootstrap?
Yes, I think there are a lot of papers. Yes. I'm not an expert, so I really cannot keep track on that. But yes, no, it's interesting. Strominger did found well. Also, Hawking this VMS symmetry at the horizon. It's an interesting area. Has mutated in something different. Still very interesting. Yes, we're not thinking about that for the moment. One thing that is important of having this very well posed problem, because we are using Hamiltonian formalism, is very robust, is the quantization problem. So in the other formulation, you cannot have the time is not well defined. It's not. So now the time is well defined and everything. So it's let's say that we are closer to quantization problems with this formulation. It's compatible with that. We are not thinking about that for the moment, but it's the correct Well, it's not. It's my opinion, but it's a robust problem. It's well defined, so that's one of the reasons of proceeding in this way. It's very hard. These computations are very hard, but the results are very robust.
Okay, so if there are no more questions, let's thank Javier again. Thank you.
Sure.
Yeah,